Hey guys, this is Loris Tech, and today I'm going to show you how to make an automated temperature fan. Before we start programming, you'll need these materials: a fan blade, a fan motor, an LM35 temperature reader, an L29 3D motor drive, 12 connector wires, an Arduino Uno unit, and a connector USB cable.
This is Emille Joseph, and I'll show you how to construct the temperature-controlled fan. You'll need the materials that were mentioned earlier in the video. So, we'll start by connecting the motor pins to the fan motor. Connect the first pin, which is the data input, to input 3 of the motor driver. This allows pin 1 to receive data from the Arduino, whether to turn on or not. Let's connect the second pin to pin 6 of the motor driver, connecting back to the Arduino to say that it's on. Now let's connect the LM35 to the breadboard to allow the sensor to communicate between the LCD and the Arduino. The flash side of the LM35 is front and will reference left to right from the front side. The left pin is the input of the LM35, connected to the 7th pin on column D. The middle pin will be connecting with the LCD to display the temperature, connected to the 8th pin of column D on the breadboard. Finally, the last pin is the output, where the temperature readings communicate with the Arduino, and this is how we will be connecting. It has several connections to different devices and pins. We'll start off by connecting all the direct pins from the LCD to the Arduino, including data, input, output, and power. The ground is the input of power from the Arduino to the LCD. Connect this to the ground pin on the LCD and the ground power pins on the Arduino. Next is the VCC, which is the output of power from the LCD, back to the Arduino. And this is to be connected with the VCC pin on the LCD and the 5-volt power port on the Arduino. Our SDA and SCL are the communicate data to and from the Arduino. The SDA is the data input from the Arduino. Connect this to the SDA port on the LCD and pin 4 of the Arduino's analog pins. The SCL is the data output, which sends data back to the Arduino, connected to the SCL port on the LCD and pin 5 of the analog pin.
We'll be using an Arduino unit to program this. We'll start by starting up the Arduino programming sketch. To start off, we have to include the programs for our LCD and LM35 sensor because they are not included in the sketch. We do this by writing hashtag include lm35.h and liquidcrystal.h. Our motor pins are used as integers from the L29 3D. To communicate the temperature from the LM35, we have to set them as integers. Type int motor pin 1, the first motor pin, equals 6, which means we are setting pin 6 on the L29 3D for motor pin 1. Now we'll do this to the other motor pin. Type motor pin 2, the second motor pin, equals 3. We have now set the third motor pin on the L29 3D for the second motor pin. Finally, we have to activate the fan motor to communicate with the L29 3D. We do this by typing int enable equals 5. We must now declare the constant variable, so the behavior of the variable is a read-only variable. It can't be changed. This secures the temperature value, not changing unless the LM35 reads a different temperature. We do this by typing const int sensor. The variable is dependent on the sensor. We'll call this variable A1. The temperature sensor is a very accurate sensor, which can read in decimal points. We'll set the temperature so it can read with decimal places. This command is called float, which is able to read the value in decimals. It works for most sensors. We'll code this by saying float temp to read the code with decimal accuracy. Because the LM35 reads in voltage, we'll also float the value from the LM35 to create a more accurate reading. We do this by typing float val. Reach the void setup, where the code will run this once. It doesn't need to be repeated. We must now set up what pins will be set to the inputs and outputs so the data can communicate with the pieces. our motor pins will behave as outputs because they are receiving data from the mini controller. We write this by typing pin mode to configure a specific pin to behave as an input or output. Then we say motor pin 1, the first motor pin, and output to declare it as output. We do this again for motor pin 2. We also have to set up the sensor and declare it as an input to the Arduino. We write this as pin mode, then sensor, because we're using our sensor integer, and say input to navigate the data to the sensor. Afterwards, we have to initialize the LCD, otherwise it won't function. We do this by typing lcd.begin and their display dimensions to initiate the LCD display. We also have to initiate the serial communication. This establishes a connection between the digital pins and the Arduino. We do this by typing serial and .begin to initialize the connection. Now, this is where the code will start to loop continuously, as it's constantly checking and measuring the variables to check for a change. We'll start by coding the sensor to read the temperature. We say this by typing our VOUT value is analog read, which tells the sensor to constantly read the temperature at whatever pace it does so. Unfortunately, the LM35 sensor doesn't directly measure the temperature, rather in millivolts, which is 10 millivolts per degree Celsius. We can convert this by coding the value of the measured voltage of the LM35 to divide its value by 10. The code is written as our VOUT value equals VOUT divided by 10 to convert the voltage reading into degrees Celsius. Let's now program the LCD display for the project. We'll start by setting the position of the temperature reading. We do this by saying lcd.setCursor 10, meaning there's nothing on the bottom row and the temp reading on the top. Also, we have to display temp and C on the screen so you know where the temperature is. Type lcd.print temp and lcd.print C to display these figures on the screen. Finally, we'll declare where the fan state will be located. Type lcd.setCursor 1. Finally, the fan will have two main functions, if the temperature is above or below 23 degrees. This is an if statement, which means if a certain variable is read, a function will happen in accordance to the if statement. If the temperature is below 23 degrees, the motor will not spin and display fan off on the LCD. We code this by writing if temp is less than 23, digital write motor pin 1 low, and digital write motor pin 2 low, to declare that most motor pins will be off. We also write lcd.print fan off to display off on the LCD, and lcd.print 1 to position this on the bottom row of the LCD display. If the temperature reads above 23 degrees, the fan will spin and the LCD will display fan on. We do this by coding if temp is greater than 23, digital write motor pin 1 high, and digital write motor pin 2 low, to declare that one pin is off while the other is turning rapidly. We also write lcd.print fan on to display on the LCD, and lcd.print 1 to display this on the bottom row. Just to allow time for the LCD to display at a comfortable rate, we'll add a delay of 100 milliseconds after each if reading. In the end, the temperature fan didn't work. We verified the code and uploaded it to the Arduino, which was successful, however nothing happened. There are several possibilities for this complication, these being a valid yet faulty program, faulty connections, or faulty parts. Our first issue is estimated to be the main concern of the project, a faulty program. As seen here, The LCD display states that there was no function to this code. Although, when we had possession of the actual Arduino project, there was no error, suggesting that in order for the code to work, it actually has to know where the pins are. This also brings up the thought that the code is somewhat reliable on the actual Arduino setup, meaning that the reason the code didn't work was probably of a miscoded port, statement, or variable. Next time, if this was the concern, the code must follow exactly what the construction displays, perhaps constructing the project, then coding, which my group didn't do. We coded and constructed at the same time, creating room for error, although we had minimal time. Another possible complication was the construction. There may have been a possible circuit or port of the device that was misplaced. The construction concept was retrieved from an online source that provided a diagram and code, which was edited for our purposes. Next time, the construction must sync with the code, giving minimal chance of error. Finally, the last possible concern for the fault project was the parts involved. We'll start with the LCD. When we uploaded the code, the LCD displayed nothing. It was on though, highly suggesting that the LCD's character display was faulty. This was tested using another code which was supposed to display hello. It didn't work either. Next is the LM35 temperature reader. We were supposed to receive a DH22 temperature sensor because it was more preferable than the LM35. Its readings are more accurate and immediately senses the temperature, not voltage. It didn't deliver it to us because our advisor couldn't get a hold of it. We tested it for readings. It was working, suggesting that the LM35 wasn't the problem. The motor fan couldn't have been the error. We tested it via battery and another Arduino project. It worked perfectly. The last possible part, possibly responsible, was the motor drive. It wasn't tested, creating probable concern that this part wasn't working. The project didn't work because of several possibilities. Next time, all the parts should be checked. The construction diagram should be verified by another source, and the code must be coded accordingly to the diagram to prevent any possible contingencies.